Good evening. Welcome to the tutorial session, lecture 5 of ME78 Thermodynamics course conducted by NPTEL. I am Priyanka Rajeev. I'm a student of Department of Mechanical Engineering, IIT Kanpur. Today we will be discussing week 4 revision questions and week 4 assignment questions. Okay, so we'll start with the first question. So these are all based on the second law of thermodynamics. Um, so revision questions will revise the concepts and will give a basic, revision or like we can look back to the week 4's lecture material with this thing. Okay. So first question is, a person was asked to state second law of thermodynamics. Their response was entropy of the universe increases. Is this a correct statement of the second law of thermodynamics? This is incomplete statement. So this is something which is like derived from the second law analysis of various system, and then we come to the conclusion. This is a general conclusion that general outcome that we are speaking about. So entropy of the universe increases is majorly when we are speaking about spontaneous processes. Um, that is when we are talking about this sort of a sentence, and it has relations to second law. We can relate this to second law, but it cannot be a standalone statement when it comes to um, when you are asked to explain second law. So second law, we have to take either closure statement or Kelvin-Plank statement in a practical form, uh, or like in a practical form, we can say like no process is possible whose only result is to transfer heat from cold to hot, or no engine can have 100% efficiency. Right. This is the layman way of saying the second law of thermodynamics connecting to closure statement or Kelvin-Planck statement. So this should be the essence when we are speaking about second law of thermodynamics. So idea of entropy when we are speaking about entropy of the universe. Universe means system plus surrounding, the whole of the universe when we are speaking. Uh, it should not be um, like the idea of entropy must not decrease um is is a consequence of second law, but it is not a usual direct statement when we are talking about fundamental statement of second law. So the statement is conceptually correct, but like total entropy in an isolated system does not decrease. That is a correct concept, but in conventional way, this is not the second law's fundamental statement. Okay. Now, second question. Consider the statement: a heat engine working in a cycle cannot have 100% thermal efficiency. Do you agree that this is a correct statement of second law of thermodynamics? Okay, so yes, this is essentially a direct expression of Kelvin-Planck statement. Um, so there is no engine operating in a cycle that converts all heat inputs into work output with no heat rejection. So this is how we will be correctly explaining Kelvin-Planck's form. So that's the correct statement. Now, next one, an inventor provides a design and asks you to check its compliance with the second law. So, what is your first check? So, you can check, okay, so you can check whether the process is happening from, uh, we will be having this test of perpetual motion machine, right? Of the second kind, of the first kind was there. First kind is violating the first law of thermodynamics. Second kind, so you can check if this is the sign of perpetual motion of second kind machine. Uh, the simplest check is to check if it is violating the Kelvin-Planck statement, which is like 100%. Does it have 100% efficiency? If it is there, then there is some kind of a violation happening in the second law of thermodynamics according to the Kelvin-Planck statement. Then if not, Clausius statement wise, if you're checking, like, is the heat is the machine converting or taking heat from cold to hot without an external work being provided. So that can be checked. So that is the best way to check whether a new device, when somebody is showing you, if that is in accordance with second law of thermodynamics or not. Then fourth question, is it possible to make a heat engine that exchanges heat with only one reservoir and converts 40% of that heat to work? Okay. A heat engine that operates only with single reservoir, that means only one source, or there is no sink, then that is by second law is not possible to produce a net work. Okay, I mean work. Okay, it cannot produce work. So according to Kelvin-Planck statement, it is like you have to have a machine which can reject some heat to a lower temperature, that is sink. If you have to run that machine in a cyclic manner, okay, if that machine is supposed to run in a cyclic process, then there should be a lower temperature reservoir or a sink in order for that machine to reject the heat. Okay, so you cannot have a single reservoir engine that produces work output, uh, be it any percentage. Here it is given 40%, that is be it any value of percentage, but it doesn't matter. It doesn't work that way. Okay. Then the fifth question, give the example of a process where the entropy of the final state is less than the initial state. Okay. So give the example of a process where the entropy of the final state is less than that of the initial state. Okay. So a process can have local decrease in entropy within the system. Okay. Where will that be compensated? That will be compensated in the surrounding. So surroundings experience a greater increase in entropy, and system, when you're observing the system, you will see that, okay, entropy is decreasing in some processes, but the effect of entropy or the second law is happening in surrounding. Okay. Entropy of the so the total entropy of system plus surrounding does not decrease. For example, when you're freezing a liquid like water, um, so if that is done in a freezer, water's entropy is going to decrease. Okay, from like phase change is happening from liquid to solid. So solid is having a lower entropy, but freezer's coil and the coolant and everything has gained a lot of entropy, and like electrical heating. So because of electrical resistance, heating is happening in coils, and coolant phase change might be happening. If you are using some phase change material for cooling, phase change of that coolant will be happening. Might be like that PCM, that phase change material might be in liquid form, then that is getting evaporated to gaseous form. So the entropy has increased for that material. So those things are happening. So the overall entropy will always be higher, like positive, like increasing. So system itself can have lowered entropy, but second law remains satisfied when you are considering the surroundings also. Then next question number 6. A thermodynamic cycle takes 100 megawatt from a source at 1000 Kelvin and rejects 30 megawatt to a reservoir at 300 Kelvin. What is the value of cyclic integral of delta Q by T? Okay. So for cyclic integral, uh, delta Q by T is 0. So that is like well known. Delta Q by T equal to 0. Cyclic integral. So I have to use, okay, cyclic integral delta Q by T equal to 0 if cycle is reversible. Okay, for reversible cycle. Then if it is less than 0, that is irreversible, right? So now we have to do the calculations for this question particularly. So what is given as heat in Q in equal to 100 megawatt at 1000 Kelvin, and Q out equal to 30 megawatt at 300 Kelvin. Okay, we'll write it somewhere else. One second. Okay. So cyclic integral delta Q by delta T T equal to 0 for reversible process. And for irreversible process, it is less than 0. Okay. Now, the data given is Q in equal to 100 megawatt at 1000 Kelvin, and Q out equal to 30 megawatt at 300 Kelvin. Okay. So Q in minus Q out, we are taking as W, then that is equal to 70 megawatt. Okay. Now for reversible cycle, we know that this 100 megawatt minus 30 megawatt, so 100 megawatt by 1000 Kelvin minus 30 megawatt by 300 Kelvin equal to 0. That means it is this thing, delta Q by delta T, delta Q by T over the cycle we are integrating. Okay, so this is like state 1, this is like state 2. So that is what we have found, that is equal to 0. That means it is a reversible process. Right. So this is a reversible process. That means QH by TH equal to Q dot L by TL. Okay. Now, next question. Okay. Critique the statement. Statements of the second law of thermodynamics are defined for cycles only and are hence not applicable to processes. Okay. For okay, are defined for cycles only and are hence not applicable to processes. Okay, fine. So the question here is, second law is defined only for cycles or not? That is the question. Okay, only for cyclic processes, or is it applicable for other processes also? So Kelvin-Plank and closure statements are formulated for cyclical devices like heat engine, heat pumps, etc. But the implications of second law is applicable to all processes, whether it is cyclical or not. Okay. Now, in differential form, when we are talking, sorry, in differential form, when we are talking, it will be like this: delta S equal to integral delta Q, sorry, it's not equal. Delta S is greater than or equal to integral delta Q by T. So for any process, the change in entropy is greater than or equal to integral delta Q by T. So this is how we apply to any process. Okay. Now, next question. List the terms in, okay, I'll just write for all processes. Okay. List the term in the equation for entropy of a control volume. Okay, this one I'll write it in separate page. Okay. So for control volume, rate of form of entropy balance is given like this. So rate of form of entropy equal to summation of entropy at inlet minus summation of entropy at outlet plus heat transfer that is happening at the boundary times temperature, or by temperature of the boundary, plus any entropy that is generated inside the system. Okay. Or you can remove this summation and put integral signs also. This will hold. Okay. So this right here is change in entropy in control volume. This is entropy flow happening with the mass flow. This is entropy flow okay, this is entropy flow in, and this is entropy flow out with mass flow. And, this is entropy transfer with heat. And this thing is entropy generation due to irreversibilities. Entropy generation due to irreversible, or one second, irreversibilities in CV, in control volume. Okay. Next question. Other than entropy transported with flows across a system boundary, entropy in flows can occur via heat transfer across system boundary. Comment on the statement. Okay. So with this previously written equation itself, this term right here says this thing, right? Entropy transfer with heat. So mass flow will carry its own entropy like this, and heat transfer from a region at temperature T, that will carry the entropy like Q dot by T. So the statement is correct. And if there is a heat transfer across a system boundary, it can bring in or take away entropy. And it also, along with the mass flow that is happening, that will also contribute to entropy. Okay. Next question. The inside space of a vessel or bucket as the system, if you're considering, initially it is half filled with water, then some water at the same temperature is added to the bucket. Okay. Will the change of entropy during this process be 0, less than 0, or greater than 0? So you have got a vessel that is half filled with water at some temperature. Let's take this T1. Then you're adding more water at temperature T1 to it. So will the entropy change be 0, less than 0, or greater than 0? Okay. So, uh, so when you are adding water at the same temperature, uh, then there is no heat exchange with surrounding, right? Like you're not adding any heat to the mixture, uh, and there is no sort of a internal temperature gradient or anything that is happening due to the addition of water. Now, uh, this new water, what is going to happen is the volume is going to be increased in the new water, like if you're adding extra water. So but the temperature and pressure is going to remain the same if the container is not changing, right? And there is no irreversibilities happening. Like if you take back the same amount of water, the system is going to be the same. So net entropy change will be very small or 0. Like if it is reversible, either you can think of it as a quasi reversible, because when you're pouring water also, again, you cannot pour it like without any turbulence or anything, right? So some kind of agitation will be there that will be adding very negligible amount of heat to that. But if your system is not that sensitive, you can consider it as reversible or as quasi reversible, but this is a reversible process. So some small irreversibilities, like when you're pouring water, there will be splashing, there will be friction. So these things are there, but those things can be neglected in most of the cases. So it is entropy changes 0. Okay, that is the answer. Process B 0. Next question. In an ice in okay, I think it is in an isentropic turbine, the entropy of the working substance will always increase. True or false? Okay. Isoentropic means what? Like entropy changes 0. Okay. Isentropic means delta S equal to 0. Entropy of the working substance will always increase. So by definition, entropy should be constant. So this is false. Okay. For an isentropic process, delta H equal to PdV. Not necessarily. So delta H equal to PdV is happening when there is some kind of a phase change or something of that sort. For ideal gas, isentropic processes will be having. Okay, I'll write it over here. Okay, if you see, oh, 4.12. Okay, now what is written over here? Yeah, dH equal to PdV. So in ideal gas, as we know, this is going to be like TdS equal to dH minus VdP, which is equal to 0. Okay. Mm. but it does not generically uh, go to dH equal to PdV, because for an ideal gas, isentropic implies PV raised to K equal to, or PV power gamma equal to constant, right? So I'll use gamma. Okay, where gamma equal to Cp by Cv, right? So the differential form do not simplify to dH equal to PdV in general. So the statement is false. Okay, this is false. This is for isentropic process. Okay, next question. A reservoir at 250 Kelvin receives 100 joule heat from a substance flowing through a pipe, whose temperature remains uniform and steady at 300 Kelvin. What will be the changes in the entropy of the substance and the reservoir? Okay, so I'll copy this question. We will solve it in the next page. Paste. Okay. So the values data given here we have to see. So they are saying heat. So reservoir at 250 Kelvin receives 100 joule of heat from a substance uh, at 300 Kelvin, right? So 250 Kelvin receives 100 joule from a substance at 300 Kelvin. What are the changes in entropy of the substance and reservoir? So heat lost by substance at 300 Kelvin we have to find. So heat lost by substance at 300 Kelvin equal to delta S substance equal to minus Q T substance equal to minus 100 by 300 equal to minus 1 by 3 joule per Kelvin. Okay. Now heat gained by reservoir at 200 Kelvin is delta S reservoir equal to plus, because it is gained, by T reservoir equal to 100 by 250 equal to 0.4 joule per Kelvin. Now net equal to delta S equal to 0.4 minus 0.33 etc. Okay, so 33 I'll keep equal to 0.0 sorry 0.6 6 it will be going, so 7 joule per Kelvin. So it is positive. Delta S is positive. Okay, so this is how we will be calculating. Next question. Where are we? Yes. Give an example of a cycle which obeys the Kelvin-Planck statement of the second law but violates Closures inequality. Okay. So if a cycle is irreversible but still rejects some heat to a low temperature sink, it will not achieve 100% efficiency. So that obeys Kelvin-Planck. However, Closures inequality says for an irreversible cycle, it should be delta Q by T, like cyclic integral delta Q by T should be less than 0. Okay, so for instance, a real world heat engine with friction and other irreversibilities will be having this delta q, like integral cyclic integral delta q by t less than 0. It does not violate Kelvin Planck, but it violates that equality part of the Clausius statement, because it is not a reversible cycle. So any real engine that we are working uh, is doing this thing, like that equality sign of the Clausius statement um, is not obeyed. So any real engine, uh, so heat engine I'm saying, with irreversibility. Okay, next question. Identify and describe the processes that causes irreversibility. So we know many uh, processes which will cause irreversibility. One is this friction, which is like due to rough surfaces or fluid, like pipe friction and all those things. Then there is this restriction for expansion, like uh, what to say, like thermal expansion, or uh, due to pressure or something. Then if the compression or expansion process is very rapid, very spontaneous, then that will cause irreversibility. Then mixing will cause irreversibility. Then electrical resistance, due to that, if heating is happening, that will cause irreversibility. Chemical reactions can cause irreversibility. So those are the some of the examples. Now, question number 16. Prove that violation of one statement of the second law implies violation of the other statement as well. So uh, what we can say is it is already proved that Kelvin-Planck and Clausius statements are equivalent. So if one is violated, the other is also violated. So okay, so if you're checking textbook, you can see like if there are discussions with hypothetical devices, like they will be first considering that suppose this device breaks Kelvin-Planck statement, then how it will break Clausius statement, and vice versa. That kind of proof is already there. Okay. Now 17th question. Write the expression for uh, write the expression for entropy change during a process where the substance is an ideal gas. Is this statement valid for reversible processes only? Write the expression for entropy change during a process where the substance is an ideal gas. Is this statement valid for reversible processes only? Okay, I'll take it to the next page. Okay, so for an ideal gas, okay, for an ideal gas, uh, taken from state 1 to state 2, okay, 1 to 2, then we can write it like this. Delta S, or the entropy change, is Cv times log T2 by T1 plus R log V2 by V1, or delta S equals Cp log T2 by T1 minus R log P2 by P1. Okay, so this formula is derived using this ideal gas equation. and does not require a process to be reversible. Okay, so this is from ideal gas equation only. So entropy is a state function. So delta S also depends on only the end state, not path. So expression is valid for any processes. Expression valid for all processes. Or let's use this for all processes. Okay. Next question. 18. Show that second law of statement for a flow process is valid for a process where the system transfers heat to the surrounding. Is it essential that the system be in steady state? Okay. So we have seen this statement right here. Okay, I'll write it over here. So ds by dt equal to sigma m in Sn minus sigma m out S out plus integral delta Q by T plus S gen. So that is always greater than or equal to 0. Okay. So this is the second law in a control volume, which has got like entropy flow due to heat transfer, mass transfer, entropy generation, etc. So this equation is valid for steady state and unsteady state. So if steady state is happening, what will happen is this, sorry, this DSCV term right here is 0 for steady state. Okay, this is 0 for steady state. There is only change. Otherwise, this is applicable for both. But you will still track the net entropy flow with heat and mass plus irreversibility in steady state. Okay. Next question. In a machine, electric power is supplied to a device and all of that is output as shaft power. Does this machine violate the second law of thermodynamics? Okay. So if you have an electric motor that converts electrical energy into shaft work with no net heat exchange, it doesn't violate second law. So second law is talking about only thermal energy from a single reservoir into work. That is what is being like that is what is forbidden according to second law, right? So second law is talking about second law is saying that you cannot convert, I mean anybody cannot convert thermal energy from a single reservoir into work without a without losing some part of it to the atmosphere or surrounding. But here input is electrical energy. So when we are talking about heat is a low grade energy. Okay, electrical energy is a high grade energy. So both are different forms of energy. So that is something different that we are not taking into discussion when we are talking about second law of thermodynamics. So there is no violation. It is a straightforward energy conversion from electrical to mechanical, just like we know energy uh, can be transferred from one form to another. So second law specifically restricts this heat direct conversion from a single source into work with like total high efficiency, like 100% efficiency. That is what is prohibited. No, that is the simple answer. Now, comment on the statement: when the internal energy of a substance increases, then its entropy also increases. So, the answer is not necessarily. So, internal energy can increase by, for example, if you are taking a adiabatic cylinder, with no heat transfer inside or out, so heat cannot be added or taken away, then you are compressing some substance inside that cylinder. It will increase internal energy, uh, which will increase temperature, but uh, it can uh, lower the entropy of the system if it is like adiabatic and reversible. So entropy uh, depends on disorder, but doesn't mean that temperature changes or energy transfer is a guarantee to higher entropy, okay, or higher or lower entropy. Now, next question. Okay, so these are assignment questions. Question number 1. 4 situations are shown below. In the table, 4 statements are given for each situation. Identify each option as true or false with supporting reasons. Okay. Okay. So there is this uh, heat, work, and temperature reservoirs for each of the systems: System A, System B, System C, and System D. Uh, and each option talks about uh, okay, so each option talks about some violations or compliances with first law, Clausius inequality, etc. Uh, now, um, system A is a device with input heat equal to work. So whatever heat is being provided from this reservoir at T, it is converted into W. So Q equal to W is this system. Okay. So if it violates first law, it doesn't. Q equal to W. So whatever energy was there initially, that has converted to W. Uh, so that is first law is not violated. Uh, what about the second law? Second law, it is violating, like without a lower temperature reservoir, uh, with a single reservoir, it is converting heat to work. So that is not possible, right? So that there is a violation over there. System A violates Clausius inequality, violates Kelvin-Plank statement. Which one is that? So it should be obeys first law but not Kelvin-Plank statement. There can be there, violates Kelvin-Plank can be here. Okay, 2 answers are there. Second, system B, 1 second. System B, possibly a heat pump or a device is there, which is like getting a heat input and a heat output is there, and it is saying, okay, it's not saying anything about it. Okay, just a cyclic process is shown and heat is being received at a temperature and given to a lower temperature without any work. So if it is TH is lesser than TL, then this is not possible. But the other way, it is possible. Okay. System 3, again, QH equal to QL plus W is first law is obeyed. QH by QL less than TH by TL. So that is also okay. Okay, obeys first law and the second law statements. This is violating Cloche's inequality because 100% efficiency they are saying, but not first law for sure. So this is there. Now third one, it is like TH to TL. So because of temperature gradient, heat is flowing. That is like, and TH is greater than TL. So yes, that is like naturally occurring. So option D is correct. Okay. Now question number 2. A heat pump is used to meet the heating requirements of a house and maintain its inside temperature at 20 degrees centigrade. On a day when the outdoor air temperature, one second. Okay, so a heat pump is used to meet the heating requirements of a house and maintain its inside temperature at 20 degree. On a day when the outdoor air temperature drops to minus 20 degrees centigrade, the house is estimated to lose heat at a rate of 1000 watt uh, through the walls to the outside air. Under these conditions, a heat pump with a coefficient of performance of 2.5 is used to heat the inside of the house. Determine power required to operate the heat pump, a rate at which heat is absorbed from cold outdoor air, and minimum power requirement for the heat pump. Okay, so answer we will see. We'll do it in the next slide. So this is the question. Now, coefficient of power, COP, can be written as Q, so house by W input. Okay. So if house requires 1000 watt heating, so Q house is fixed to 1000 watt, then we want to find W input, work needed. So that can be found by W input. So coefficient of performance is given as 2.5. W input equal to 1000 by 2.5, which is equal to 400 watt. Okay. So power required is 400 watt. That is found. Rate at which heat is absorbed from cold outdoor air. So heat from outside, Q house, this is A, this is B. Q house equal to Q outside plus W input. Now Q outside equal to 1000 watt minus 400 watt equal to 600 watt. Okay. Next is C. So this is 600 watt. Minimum power requirement for the heat pump. So if it is a reversible heat pump between the temperatures T house and T outside, then coefficient of performance maximum, okay, equal to T house or T hot, the higher temperature, by T hot minus T cold. Oh, okay, these are all in Kelvin we have to take. So T H equal to what? 20 plus 273. 20 is what given? 20 degree and minus 20 degree. T cold or TO equal to minus 20 plus 273. So that is 253 Kelvin. This is 293 Kelvin. Now coefficient of performance maximum is going to be 293 by 20, which is equal to 40. It's 293 minus 253. So 40, which is equal to 29.3 and 47.325. Minimum power required is W minimum. So what I was seeing is, we know coefficient of power performance is Q house by W input. So if this device has got, heat pump has got maximum coefficient of power, coefficient of performance, then it will require minimum work, right? So that is what I have done. So the requirement is still 1000 watt and coefficient of performance is 7325. So that will give you 1000 by 7. I have to use calculator. Around 136.5 watt. Okay. So this is the answer. Now, third question. A coal burning steam power plant unit, a coal burning steam power plant unit operates in a thermodynamics cycle, taking heat from a source produced by burning coal, whose temperature is 1200 Kelvin. Okay. Now, if it rejects heat to a sink, which is the ambient atmosphere at 300 Kelvin. So 1200 Kelvin to 300 Kelvin. So source and sink temperatures are given. It produces 600 megawatt net output and its overall thermal efficiency is 42.5. So yeah, all the data is given. What are they asking? Calculate the rate at which heat should be supplied to the source. Then what is the maximum possible efficiency attainable? Okay, we'll solve it one by one. 4.3. Oh, okay. 4.3. Goes something like this. Okay. So first answer for A, given data, so they are asking for W net is there, Q in is there. Okay, so they have given eta equal to 42.5%, right? So eta, or the efficiency, is equal to W net by Q in, and that is equal to 0.425, right? So work output is given. Now we have to find Q in with this thing. Okay, work output is equal to 600 megawatt. So Q in equal to 600 by 0.425, which is equal to, it takes some time, 1, okay, 1412 megawatt. Okay. Next, so this is A. Second is, what is the maximum possible efficiency attainable? Maximum possible efficiency will be according to this, if we are, that will be Carnot efficiency, right? Carnot efficiency is assuming um, reversible process, and this will be, it will be the temperature of heat and heat sink and the heat sinks, like the cold reservoir and hot reservoir. So that is equal to 1 minus, temperatures are 300 and 1200. So 1 minus 1 by 4 equal to 3 by 4, that is 0.75, 75%. Okay. Next, coal burn rate. So they are saying power plant burns a coal whose heating value is 25 megajoule per kilogram. Further, burning 1 kilogram of coal releases 2.5 kilogram of carbon dioxide into atmosphere. This contributes to global warming and climate change. Determine the rate at which coal should be burnt in the furnace. Calculate the daily emission of carbon dioxide into atmosphere. This will give you an insight of how much carbon footprint we are talking about here. Okay. So coal burning rate, they're saying what? 1 kg of coal gives you 25 megajoule. Okay. Now we need what? 1412 megawatt. 1412 megawatt means joule per second. Hmm? Is required. That means over 1 second, if we are taking, it is 1412 megajoule. So for that, how many x kilogram of coal is required? To just cross multiply, you will be getting 1412 divided by 25 equal to x. So that is equal to 56.48 kilogram of coal. Okay. So you have to, the mass of burning, okay, coal is like 56.48 kilogram per second. Okay. Now we have to see the data. 1 kilogram of coal releases 2.5 kilogram of carbon dioxide. D. Okay, D part is 1 kilogram coal gives 2.5 kilogram of carbon dioxide. Okay. So 56.48 kilogram per second for 1 day. 1 day is 86400 seconds. This is the amount of coal required for 1 day. Gives x kilogram of CO2. Now find x. Find x. It is 2.x equal to 2.5 times 56.48 times 86400. It's going to be immense, like huge number. So it is 1.218 times 10 to the power 7 kilogram of CO2 per day. Very, very huge, very huge. So this much carbon dioxide emission will happen just for heating up a facility to 1200 Kelvin. Obviously, you don't need 1200 Kelvin. That is like about 1000 degrees centigrade. No, nobody wants that much heat. Only for industrial purposes we will be using that. But still, this is how much carbon emission will be happening from such an industry. Okay, so 3 is over. Now 4.4. Refer to the problem 4.3. See. Consider pump to be isentropic. Its actual power input is W act. 1 second. So everything is in reference to some problems in 3. I have to open that assignment. Okay. So W3, this question they are talking. Okay, we will take it out. Okay. It's taking some time, sorry. Okay, let it be here. So this is the question that they are talking about. Liquid at temperature theta 1 degree centigrade and pressure P1 bar enters a pump where its pressure is increased to P2 bar. If the flow rate is m dot kilogram per second, then what is the power input to the pump? So consider the pump to be isentropic. Its actual power input is, okay, I have to put this above and below. Then this, yeah. Okay. Consider the pump to be isentropic. Its actual power input is W dot ACT, kilowatt. Write the relation for shaft power input to the pump for isentropic pump, W dot S kilowatt, in terms of flow rate and inlet and outlet state properties. Okay. So isentropic pump power is given by W dot, we are using S equal to M dot H2 minus H1. Okay, where H2 is the enthalpy at exit and inlet. Fine. Now isentropic efficiency we have to find. So how to find isentropic efficiency? Eta pump equal to W dot S by W dot ACT equal to M dot H2 minus H1. So we will take this H2 as pump exit. Okay, pump exit, that is different. And then we have got the actual exit of the system, the liquid. Okay. For isentropic pump, this H2 will be there, and the other pump there will be H2 minus H1. So H2 is going to be H2 star greater than H2 star. Okay. So this is how you will be finding W app. You can just cross multiply and find. Okay. Next question. Fifth question. An evacuated CNG cylinder of volume V meter cube. Okay, this question is also from third assignment. So I have to take it from third assignment. So the other one. This is question number 3. Sorry, question from assignment number 3. And here is the question from assignment number 4. Note this one. Okay. This is the actual question. So they were explaining that okay, CNG was filled into a cylinder. So it was so what will be the independent properties of filling that gas into cylinder if we have to measure something about that system. So we identified as pressure and temperature. Now they're asking so the CNG of volume V meter cube and okay, V meter cube is being filled from a supply line where the pressure is Phi1 at the state. Specific internal energy and specific enthalpy are U1 and H1 respectively. What is the mass of gas that has been filled when the pressure of the gas in the tank reaches Phi T bar? Write the expression for calculating the final temperature and mass of gas in the cylinder and entropy change for the process. Okay. So mass calculation, it is a transient open system, so unsteady state. So if we assume no heat loss or anything, because it will be like usually CNG is filled at in a laminar flow because it's all flammable gas, you would do a mass plus energy balance from initial to final. Okay. Now from final temperature, if you want to find, if the supply is large and at state Phi1 and theta1 and the cylinder is initially empty, you will analyze the fill as adiabatic and all. Then the final temperature will be just depending on the enthalpy in. Okay, so enthalpy in is going to be your internal energy final. So from there you have to calculate H in equal to U final. So from here you have to calculate. So this is like Q equal to 0 condition, adiabatic condition only. So entropy change is going to be delta is equal to S final. Initially there it was evacuated, so it is 0. Sorry, S final minus 0. So that is like initial it was evacuated, so it is 0 entropy equal to M final times specific entropy S final. Okay. So that's that. Then the next question. 4, 5, 6th one. Write the equation for entropy change for this process. Which process? 3, 9. That is 3, 9. Okay. This question. This is 39. We have to write the entropy change for this process. Okay. Okay. So it is like fluid is flowing in a pipe at temperature theta 1 and pressure Phi1 bar. It passes through an expansion valve, after which it is pressure is dropped to Phi2 bar. The inlet and outlet velocities are comparable. Device is placed horizontally from inlet to outlet. So they're just saying it to avoid that potential energy term. The device is okay. Which two independent properties at the outlet fully define the outlet state that we have found earlier. Now, it is about throttling valve, right? So adiabatic, it will be adiabatic. So Q equal to 0. Q equal to 0. Then enthalpy remains constant. So H1 equal to H2. Then entropy increases, or it can also remain same if the process is ideal. In like a real life scenario, it usually increases because throttling is a irreversible process. Now entropy changes delta S equal to S2 minus S1. It is greater than 0 for throttling. Then and we have to compute it with the initial and final state values. Now 7th question. Okay. This also we have to get from the third. 3, 7. Okay. This is 3, 7. And our question is 4, 7. This is 4, 7. Okay, now they're saying this block of mass MA and MB were brought together in contact. They are made up of aluminum and both have got temperature theta A and theta B. And we wanted to find the equilibrium temperature back then. Now they are asking to find equilibrium temperature and entropy change also for this process. Okay. Okay. There is a relation for specific internal energy is also given. Now, equilibrium temperature with the energy balance. Energy balance equation is as follows. So, MA C theta A plus MB C theta B equal to MA C theta F plus MB C theta F, where theta F equal to MA. So you're rearranging it. Theta A plus MB theta B by MA plus MB. Okay. Now, entropy change, how to write? So, entropy change will be delta S total, which is equal to delta SA plus delta SB equal to integral TA to TF. Okay. TF MAC by T, MAC by T dt plus integral TB to TF MBC by T dt. Now if we evaluate these integrals, we will be getting delta SA equal to MAC log theta F by theta A, and delta, so change in SB is equal to MBC log theta F by theta B. Okay, so this is the solution. Now question number 4.8. So we have to refer to assignment question again. Third assignment, 4.8. Okay, for this question. Okay. So this is the question. So the question here is 3, 4. This one. So there is a construction in the pipe, that is the question. Okay. So question they are saying is a sketch of the device and the system boundaries shown. Which of the following statement is true for this process? Refer to, why we have to refer for this problem? That was not required actually. Okay, so which of the given statements about entropy generation or rates is true? So first we have to write steady adiabatic condition. Then entropy generation term will be like, so adiabatic means Q is not there, then steady adiabatic, okay, so that will be Sgen equal to just entropy input, entropy with mass inflow and mass outflow. That is the only terms that are left. So S2 minus S1 will be equal to S dot gen by M dot, okay, S2 minus S1. So that term is not here. Yeah, this one is correct. First one will hold. Now 4, 9. Calculate the entropy change. Okay, again we have to go to assignment 36411, this one. Sorry, this one right here. 49. Yeah. Okay. See that? And this one 49. Okay. Okay. So diesel generator set radiator, hot coolant from engine enters at some temperature and it is being cooled and exiting at a higher temperature. Calculate the heat transfer, we have done already. Now calculate the entropy change for air, coolant and radiator. That's the question given. So if you see here, it's going to be 36. Okay. Air will be getting in, so which is the air they are talking about? Air, coolant and radiator. Air is gaining heat from the diesel generator, so entropy of air is going to increase. Coolant, again, coolant is gaining heat from the air. Sorry, coolant is losing the temperature, so is coolant equal to less than 0, and radiator is a passive medium, so it is like almost same temperature all the time is radiator, so it is going to have approximately equal to 0 entropy, T equal to constant. Okay, so overall delta S equal to total is greater than or equal to 0. So if you want to calculate delta S air, that will be integral delta Q air, so heat gained by air and temperature of air, at what temperature it is gaining. Delta S coolant will be integral delta Q coolant by T coolant. Okay. So radiator is just a conductor, so delta S for radiator will be 0. So that's for it today. I hope I have completed all the assignment question. So if there is any doubt, please feel free to contact me. Thank you for this session and listening to this session. Thank you.